Hello, this is Mr. Lee's physics class. I'm Mr. Lee. In this video, we are going to talk about the kinetic and potential energy of the particles in matter. Be careful, it's just the particle that we're talking about. For example, when I speak of the kinetic energy, I don't mean that the body itself is moving. Rather, it's the particles in that body which are moving, while the body itself can be at rest or moving. It just doesn't matter. Similarly, when I talk about the potential energy, it's not that the body is at a height from the ground, because it's the potential energy of the particles that I'm concerned about, not that of the body itself. So let's start. The kinetic energy Ke of the particles describes how fast they are moving or vibrating. A quick refresher here, the particles in solids vibrate but move around in liquids and gases. This is to say, the faster the particle's motion, the higher the Ke of the particles. Macroscopically, this relates to the temperature of the matter. The faster on average the particles move or vibrate, that is the higher the average Ke of the particles, the higher the temperature of the body. While the Ke of the particles is intuitive, why would there be potential energy at all for particles in a body? Well, let's put particles aside for a moment and take a look at a block on Earth. If it is released here, it accelerates downward, which implies that its kinetic energy Ke increases. Such an increase in Ke must have been converted from energy of some form, and that's what we named the potential energy Pe. In the logic above, there are two key points you should note. First, the root of potential energy is that the Earth attracts the block. Without such a force, even if the block is released, there wouldn't be any acceleration and therefore any change in Ke. And this implies no Pe stored at the beginning. Second, the farther away they separate, the greater the potential energy stored. That is simply because the farther away they are, the greater Ke is gained when the block arrives the ground, and that must have been converted from a greater Pe stored at the beginning. Generalizing this, it just means that anything attracting each other must have potential energy stored. And the farther they are and the stronger the force, the greater such Pe is stored. Now it's straightforward to see why particles in matter possess potential energy Pe. It's just because there are various forces between the particles. And from our arguments above, the farther they are separated, generally the greater the Pe is stored. So the Pe of the particles of a body in its gas state is higher than its Pe in liquid state, and in turn higher than when it is in solid state. In short, the Pe of the particles in matter depends largely on its state. The unit of energy is joule, written as capital letter J in calculations. As with other units, we may put prefixes before it. Like kilojoule kJ is 10 to the power 3 joule or 1000 joule, megajoule mJ is 10 to the power 6 joule or a million joule. Gigajoule GJ is 10 to the power 9 joule or a billion joule. Another term to know is the internal energy of a body. It's defined as the sum of the kinetic energy and potential energy of all the particles in that body. Loosely speaking, it is the total energy of all particles in the body. Mathematically, we can write this. Internal energy is equal to the total Ke of all particles plus the total Pe of all particles. Now, suppose there are n particles in the body. Their average Ke is equal to the sum of their Ke divided by the total number of the particles n. Rearranging, we have the total Ke of the particles being equal their average Ke times n. And so this part of the expression can be written as this. By the exact same logic, the total Pe of all particles is equal to their average Pe times n, the total number of particles. And so this part of the expression can be written like this. There are several deductions among others that you should be well aware of. If you increase the temperature of a body, its internal energy increases. The reasoning goes like the following. Supposedly, for the same body, its number of particles is fixed. As the temperature increases, the average Ke of its particles increases. So, this part which represents the total kinetic energy of all particles increases. If the state of the body is not changed, the average PE of the particles remains unchanged. This is due to the point mentioned earlier here that the PE of the particles depends largely on the state of the body. Now that this part increases and this part is unchanged, it's obvious that the internal energy of the body increases. Of course, you may ask, what if the state changes? Well, even so, its state can only change in this direction because we are considering increasing its temperature. Then the average PE of the particles would only increase. This is because we have concluded a little earlier that the average PE of the particles in a body is the highest when it is in gas state, followed by liquid state, and then lowest in solid state. So, whichever the case, this part, the total potential energy of all particles would only stay unchanged or increase. If this term increases and this term is either unchanged or increased, then it follows that the internal energy must increase.